Hello, welcome to your lesson on probability rules. This is part one or lesson one of a 3-video series on this topic. Today, or in this lesson, we'll talk about the probability OR law and the AND law. We're going to begin with some examples, which will then lead to the formulas we need to know from this section. Let's begin with this. As you know, everybody carries around a sack with them, and that sack has cubes in it. You're probably holding your sack of cubes right now. In this sack, in this example, there are 3 red cubes, 4 black, and 5 blue cubes. A cube is selected at random from the sack. What is the probability of selecting a red or a blue cube? Okay, so just looking at that, the answer is probably obvious. You reach in there, what's the chance that you're pulling out a red or blue cube? Well, you have your red cubes and you have your blue cubes, and you see how many you have out of the total. But we're going to break this one up into parts, and you'll see why it has to do with our formulas. So probability of red or blue is the same as probability of red union blue. So the word OR in probability typically means union. And probability of red or blue or union blue is probability of red plus probability of blue. Again, we have 3 reds, 5 blues, so that's 8 cubes out of 12. So we can just add up the reds and blues to get what we need. And that's what we're doing here. We're saying there are 3 out of 12 reds and 5 out of 12 blues. Therefore, that is 8 out of 12 in total. Gives us our probability, which reduces to 2/3. So 2 out of every 3 in here are either red or blue. Okay, looking at another example, or sorry, looking at the same one in terms of Venn diagrams, let's see what it looks like. By the way, all these videos have lesson notes that you can print that will make the taking of notes much easier for you. I would suggest printing those out. Okay, so the Venn diagram for this one is we have a universal set of 12. That represents the 12 cubes in total in the sack. Then in that sack we have subsets or sets. Sets are red cubes 3. Set B, which I'm going to use for black cubes, is 4. And then BL, I'm going to use for blue cubes, 5. So now I noticed I just made a mistake, because here I called B blue, but now I'm calling blue BL here. Anyway, that blue-black thing is a little confusing here. But anyway, we have 3 reds, 5 blues, and in total this is 8 out of the 12 inside this sack. Notice the circles, which is important, are not overlapping because there is no intersection. For example, a black cube cannot be a red cube at the same time. The intersection would imply that they can be both at the same time. That's impossible. Okay, now we have a standard kind of probability problem. We have a deck of cards. As you may know, a deck of cards has what is called 4 suits. There are the hearts, the clubs, the diamonds, and the spades. Each suit has an ace, which can be considered like a 1, and then 2 all the way through 10. And then there are 3 face cards, a jack, a queen, and a king. All the suits are identical in this way. There are 13 cards in each suit. Alright, so we have a situation where we're drawing 1 card randomly from a pack of 52 cards. What is the probability it is an ace or a king? So we're looking at these aces here, we're looking at these kings here, and just like in the last example, the answer might be obvious. Well, we have 4, we have 8 total possibilities out of these 52 cards. But we're going to break it up as well. We have probability of ace or king, so union. We're going to do 4 out of the 52 are aces, 4 out of the 52 are kings, so therefore we have 8 out of 52 in total, and that reduces to 2 out of 13. The 2 out of 13 should make sense because we have in one suit, for example, hearts, we have 1 ace, 1 king, so 2 out of those 13 meet the condition of being an ace or a king. All right, let's do that one as a Venn diagram because it's a little bit different than the last one. We have a universal set of 52 cards. In that universal set, we have aces, which are 4 of them, and we have kings, which are also 4, meaning there's 44 other cards. But in total, again, no overlap because a card cannot be an ace and a king at the same time. But we have a total there of 8 out of 52 cards that are aces or kings. Okay, back to the cards again. This time, what is the probability that we draw a queen or a diamond? Here are our queens, 4 of them. Here are our diamond cards, 13 of them. So the probability should be 4 plus 13, right? 17 cards. Well, no, because we are looking at this overlap right here. This queen is both a queen and a diamond, so we shouldn't count it twice. So to find the probability of queen or diamond, queen union diamond, we have 4 queens out of 52 cards plus 13 diamonds out of 52 cards. But again, that would not be the right answer, because by doing that we have counted this queen twice. So we're subtracting it once, 1 out of 52, and now that gives us 16 out of 52 cards instead of 17. So that intersection, we've talked about that a lot when we did sets before, but it's important to know that that intersection we have to subtract away. That reduces to 4 out of 13. Now let's take a look at that one as a Venn diagram. We have our universal set, 52 cards. We have our queens, 4 of them. We have our diamonds, 13 of them. However, they overlap because there is one card that is both a queen and a diamond, so it goes there, leaving 3 queens here and leaving 12 other diamonds here. So we were looking for the union here, and as you remember, the union is everything that's within these two circles. So the union is 3 plus 1 plus 12, which is 16 cards in total, not 17. If you just added 4 plus 13, we'd have 17. Too much. All right, just to summarize some key vocabulary related to this, in the first two examples, the events that occurred could not happen at the same time. In number 1, a red and blue cube could not have been chosen at the same time. In number 2, an ace and a king could not have been chosen at the same time. Events such as those which cannot happen at the same time are called mutually exclusive. Events like that are called mutually exclusive. Events like that are called mutually exclusive. All right, I had to say it 3 times. That's a key term in probability. Make sure you memorize that term and what it means. However, in number 3, a chosen card can be a queen and a diamond at the same time. Events that can occur at the same time are called inclusive. All right, let's look at the formulas now. So for disjoint, which are mutually exclusive events, here's a diagram of that, right? We had the 2 circles that have no intersection. They are mutually exclusive. So for these events, the probability of A or B is the probability of A union B. And we find that simply by adding that probability with that probability. Okay, that's what we did in the first 2 examples. For the probability of A and B for these kinds of events is the intersection. And as we can see, mutually exclusive events have no intersection. So A and B, if one item from the, anything from the sample space cannot be A and B at the same time. There is no intersection. So the intersection is 0. Again, simple idea here, but very important idea in probability, because often you will be working just with numbers, you won't have Venn diagrams, and in the end you have to decide, maybe are 2 events mutually exclusive, and if you can find out that their intersection is 0, you can then conclude that they are mutually exclusive. All right, going to inclusive events where we have an overlap, the probability of A or B, which is A union B, is now probability of one of them plus the other, but you subtract away the intersection. So we've seen this formula before. Add the 2, subtract the intersection. Probability of A and B, this formula is now the intersection formula. It comes from looking at this formula and moving 2 things around. Think of this equation here algebraically. You can move this intersection to the left side of the equation and this to the right side of the equation, and you'll end up with this. Basically, the union and intersection have swapped places in the formula. That's our intersection formula for inclusive events. All right, let's use those 4 formulas. They are 4 key formulas in probability theory. First of all, we're going to have this mutually exclusive situation. We have 10s, we have face cards, there's no overlap. What is the probability you select a 10 or a face card from a deck? Please challenge yourself to set this up using a formula before you use any numbers. Okay, here we go. So we have probability of 10s or face cards. And since this is mutually exclusive, we simply add the 2 probabilities. Probability of a 10 plus face cards, so there are 4 10s, 12 face cards. In total, we have a probability of 16 out of 52, which reduces to 4 out of 13. Again, this should make sense because in one suit, for example, hearts again, we have 1 10 and then 3 face cards. So 4 of the cards in the hearts meet these conditions, so 4 out of the 13. Okay, Second problem, what is the probability you select a face card or a spade from a deck? Okay, you can see that in this diagram here, these are not mutually exclusive. There is an overlap or intersection. These three cards are both face cards and spades. Here we'll have to use the union formula again because we're talking about OR, but this time we're using the expanded union formula to subtract away the intersection so we don't count it twice. So probability of face cards plus probability of spades minus the intersection, and we get our probability of 22 out of 52, which reduces to 11 out of 26. Moving on, next problem. This is a good one. We have 40 items on the menu at a Thai restaurant. Of these items, there are 14 spicy items, 9 vegetarian items, and 23 items that are neither spicy nor vegetarian. Begin by drawing a Venn diagram, and then find the probability using the formulas that an item selected is spicy and vegetarian. All right, here we are back again. Hopefully you've tried this out. Let's check your work. We have our union, which is all 40 menu items. Sorry, not union, our universal set of all 40 menu items. On that menu, we have 14 spicy, a set of 14 spicy items, and then we also have a set of 9 vegetarian options. It never said that some vegetarian options are also spicy. So how do we know there's an intersection? Well, the way we know is it tells us there are 23 items that are neither spicy nor vegetarian. So those go here. Now when we have 40 in total and 23 that are neither of these, so 40 minus 23, that means there must be 17 items in total here. But if we add 14 and 9, that's more than 17. So that's how we knew that there must be an intersection. And again, these must be 17, and these two add up to 23. So that means 23 minus, sorry, these add up to, oh, they must add up to 17, right? So we know there's a difference of 6. So that is the intersection. That was the start. So we've already answered the question. Basically, it says find the probability an item selected as spicy and vegetarian. Well, that's it right there. There's 6 items that are both spicy and vegetarian. We have the answer from the Venn diagram, but again, today we're concentrating more on the formulas. So we're going to see if we can go and use the formulas to calculate the same value. Let's put in some more values. If that's 6, this is 8. And if this is 9, then this is 3. Let's use the formula for intersection because that's what this is asking for items that are spicy and vegetarian. So spicy and intersection vegetarian. Remember that formula is you add all the spicy items with the vegetarian items and then you subtract away the union. Remember again, that was the reverse of the union formula. Okay, let's put the numbers in there. Spicy items, 14 out of 40. Vegetarian items, 9 out of 40. Minus the union. The union again is everything in these circles. That means 8 plus 6 plus 3, which is 14, 17, so minus 17. And that gives you 6 out of 40. Again, that matches what we saw in the Venn diagram. There are 6 items in the middle here. Okay, great. So last problem. At a house party, there are 27 kids, 68 adults. Sketch a Venn diagram and find the probability of K intersection A. All right, now that you've tried, let's take a look. The Venn diagram for this one is pretty simple. We have universal set. We don't know how many people there are at the party necessarily, but we do know there are 27 kids and there are 68 adults. There is no overlap, because an overlap would imply that a kid and an adult can be the same person. That's impossible. Kids are kids, adults are adults. There is no kid that is an adult. So what that tells us is when we're looking for the intersection, like in this problem, again, it's one of those situations. These are mutually exclusive, so therefore they will have no intersection. So the intersection is kid and adult. There's nobody who is both at the same time. There is no intersection. It is 0. Great, you've finished video 1. There are 2 more videos in this video series on this topic. Please go to video 2 now.